A token arrives at a service. The service checks the signature. The signature is valid, the check passes, and the request is processed. The user is not who they claim to be. Nothing in that sequence was a mistake. The verification step executed correctly. It found what it was looking for and returned the result it was designed to return. The problem is that the system treated that result as the answer to a question verification was never designed to answer. Verification is one of the most consequential misunderstandings in security, not because engineers implement it incorrectly, though they do, but because they misread its contract. They build systems that treat a passing check as a guarantee of trust. Verification does not provide that guarantee. It provides something narrower, more specific, and considerably easier to satisfy than most systems assume. Understanding that gap starts with understanding what a verification check actually confirms. When a service verifies a JWT, it confirms that the signature over the payload matches the signing key it expects. That is the check. It does not confirm that the issuer of the token is the identity provider the service was configured to trust. That is a separate validation against the issuer claim, which many implementations skip entirely. It does not confirm that the token was issued for this specific service, rather than a different one sharing the same signing infrastructure. That is the audience check, also commonly omitted. It does not confirm that the claims inside the token reflect the user's current state, rather than their state at issuance, 40 minutes or 6 hours ago. It does not confirm that the algorithm used to produce the signature is the one the service intended to accept. Consider what that omission means in a shared environment. A developer builds a service on a shared identity platform and configures it to accept any token the platform signs. A second service on the same platform is compromised. The attacker issues tokens, claiming to be a high-privilege user of the first service. The signature verifies. The issuer claim says the platform. The audience claim is absent. The first service accepts the token and acts on the claim. Each of those validations is a distinct question. Signature verification answers one of them. Systems routinely act as though it answered all of them. TLS certificate verification follows the same structure. When a client verifies a server's certificate, it confirms that the certificate was issued by a trusted certificate authority and that the cryptographic chain from leaf to root is intact. It does not confirm that the hostname on the certificate matches the domain the client intended to reach. Hostname verification is a separate check, and a significant number of applications disable it during development, under pressure from connection errors, and never restore it before shipping. It does not confirm that the certificate hasn't been revoked since issuance, which requires a separate query to a revocation service that most TLS clients skip by default or fail silently when the service is unreachable. A certificate can pass verification and still belong to a server the client has no reason to trust. Code signing follows the same pattern again. A signed binary confirms that the code matches the private key used to sign it. Origin, in the narrow sense that origin means whoever controlled that key, at the moment of signing, produced this output. It says nothing about whether the build environment was clean, whether the key has since been compromised, or whether the dependencies bundled into the binary came from legitimate sources. This is the verification gap, the distance between what the check confirms and what the system acts on as though the check confirmed. It has produced documented failures at scale. In 2014, Apple's SSL implementation contained the goto fail bug, a duplicated goto statement that caused the certificate verification function to exit before the signature had been checked, returning success regardless. The check completed. No signature was verified. The flaw had shipped across iOS and OS X for months before it was found, and every TLS connection made over that period appeared verified without being so. In 2020, the malicious update distributed through the SolarWinds Orion compromise was signed with SolarWinds' own certificate. The signing key was legitimate. Endpoints that verified the signature received a clean result. The build environment that produced the binary had been compromised 9 months before the update shipped. 18,000 organizations installed it. GTT algorithm confusion attacks exploit the property directly. An attacker submits a token with the algorithm field set to none, a value the specification permits in certain contexts, and that libraries failing to explicitly reject will accept. No signature is present, the check passes. The service acts on the claim. The verification step was not bypassed. It completed correctly against an input the attacker constructed to satisfy it. The consistent pattern is not that verification fails, it is that verification passes, and the system then acts on a conclusion verification never drew. The claim is current, the issuer is legitimate. The token applies to this service. None of those conclusions follow from a valid signature. They follow from an assumption the system imported without noticing. Verification is a precise instrument. It answers a precise question about cryptographic consistency between a claim and a key. It does not establish that the key was in the right hands, that the claim is still current, that it applies to this service, or that the issuer should be trusted at all. Those are separate questions. Most systems do not ask them separately. They ask one and assume they have asked the rest. The attacks ahead are not attacks on verification. They are attacks on the assumption that verification and trust name the same thing.